Hey everyone, let's see, we're going to continue our study of R3, and there's a couple of concepts that we want to cover this time. So first what I want to talk about are lines in R3. Now, you don't need to write this part down, but I mean, a line in the plane, everyone in this class is familiar with how that goes, right? If you know the slope of the line and one point that it passes through, right? Then you can write down an equation for the line. That's all you need to know. That completely determines it, right? So essentially, if you describe how the line is slanted, right, by the slope, and right, if you just describe the slant, well, there's an infinite number of lines that have that same slant, that same slope. But then if you say, I'm thinking of the line that has a particular slope, a particular slant, and passes through a particular point. Say if I want it to pass through that point right there. If you specify the slope and then say I want it to pass through that point, then there's exactly one line that satisfies that. So that's why in R2, a line is determined by the slope and a single line that it passes through. Now, when we get into 3 dimensions, slope suddenly has no more meaning, right? I mean, what is slope? Well, okay, so it's rise over run. But if we want to talk about in 3 dimensions, if we wanted a line, well, what exactly is rise versus run when you've got 3 dimensions? Well, it doesn't make sense anymore, right? Rise over run is really a 2-dimensional concept, and so we need a 3-dimensional concept, right, to describe lines in R3. And here's what we do, is we say, okay, well, all right, in R2, we had this notion of slope. Instead, let's think in terms of direction. Right? So if I was to say, all right, I'm thinking of a line that travels in this particular direction, right? Well, now in 3 dimensions, right? So now there are an infinite number of lines that satisfy a direction, right? I'm thinking of a line that points in a particular direction, right? There's an infinite number of them. But then if I say, I'm thinking of a line that points in this direction, right? And passes through this point right here. Whoops, I think I was pointing out the shot there. Point passes through this point, then there's exactly one line. So what we're going to do is replace the concept of slope with the concept of direction. Now, how do we get a concept of direction, or how do we define direction? Well, we do that with a vector. And so for 3 dimensions, I'm going to write all this down in a second. In 3 dimensions, we replace the concept of slope with the concept of direction vector. And so a vector will give us a direction, and then so we say we want this direction passing through this point. That will uniquely determine the line. Okay, so let me write this down, right? In R2, a line is determined by slope plus 1 point, right? That's the picture I was drawing here. Determine point, or give me a slope, give me a point. That completely determines the line, right? In R3, slope has no meaning, so we replace this. So instead, we use what's called a direction vector. Okay, so now we want to derive, so I want to make this all precise, right? So let's take a line. So let's let capital L be a line in R3. And I want to pick a point, let's call it P0. So let's say and let P0, which will be x0, comma y0, comma z0, be a point on the line capital L. And then one more thing, so we also let, let's call it V. This is going to be my direction vector. Do I need to specify who it is? No, I guess not. We can just call it V. So let's let V be a vector parallel to capital L. Remember, parallel means just pointing in the same direction, or following the direction of the line L. So let me draw the picture here. Right now we're in three dimensions, right? So I've got a line. Let me put a little bit of depth to it. So let's draw the line, and then right, so here's my line L. I need a vector that is parallel to the line, so it doesn't actually need to live in the line, but it needs to be pointing in the same direction. So typically, all right, I like to have my vectors emanate, or at least my direction vector for now, emanate from the, what am I trying to say here? From the origin, right? So I'm going to choose the position vector for V. Right, so here's my vector V, here's my line, and then I need a point, and I'm going to call this point P0. Okay, now what I want is an equation or some sort of way to characterize, to capture all possible points living on this line. So let's say that I have another point. Excuse me. Let's say P on the line. So if P equal to X, Y, Z lies on capital L, well then I can think of the vector that joins P0 to P. So let's say what? Oh, right. So let's go like this. If P lies on L and R, comma R0 are the position vectors of P and P0 respectively, then, all right, so what can we say about the vector that goes from P0 to P? And do I want to give that a name? Yeah, call it A. So then the vector A from P0 to P. Okay, so here's my vector A, right, joining P0 to P. Now, what can we say about this vector A versus this vector V? Well, since V is parallel to the line L, A is a vector that's parallel to V, which means that A is a scalar multiple of V. All right, so then, okay, so yeah, there's actually two things. So first of all, notice that A has to be a scalar multiple of V. Also, notice that A is one of the vectors that completes this triangle right here. So in fact, the vector, so let me label these. Here is R0, and here is R. So R0 plus A equals R. All right, so let's say it like this. So then the vector A from P0 to P is parallel to V. So this means, so we can say thus, A is equal to T times V for some T, right? A has to be a scalar multiple of V. So since R is equal to R0 plus A, we have R is equal to, so now I'm going to substitute for A, R is equal to R0 plus T times V. And that equation right there is known as the vector equation of L. And I don't think I've said this, or at least I haven't written it down. So V is the direction vector of capital L. So now in R3, if you want to talk about a line, what do you need to know? You need to know a direction vector and a single point on the line, and that completely determines it. When you have that, you can just write down the vector equation for the line. All right, so let's try an example. And before I do the example, let me just point out what's going on here. So what we would like to know, right? An equation for a line is supposed to allow us to figure out what points live on the line and which points don't. So how does it work here? Well, each time we take another value of t, it's going to give us a position vector r corresponding to another point on the line. So for example, when t equals 0, we get r equals r0. So it tells us that r0, the position vector, right, corresponding to p0, right, it tells us that p0 lies on the line. Anytime or each time I choose a new t, it gives me a new vector, and so what it does is it gives me a new tip, right? Think of the tip of the vector as living on the line. So every time I choose a new t, it spits out a new point on the line. And when you let t run through all real numbers, it spits out every possible point that's on the line. So let's try an example. Hopefully this will clarify a bit. So, so let's let L be the line through the points so let's do 1, 1, 1 and 2, 5, 0. What I want to do is find the vector equation of this line. So find the vector equation of the line L. So remember what we need. We need a single point and a direction vector. So here's the idea. We've been given an equation of a line. Yeah, this is sitting in R3 now. So I've got the point 1, 1, 1. I've got the point 2, 5, 0. What do we need to determine the line? We need a vector that's parallel to the line. Ah, there's one right there. How about the vector that goes from 1, 1, 1 to 2, 5, 0? That will be my direction vector. And then I also need a point that lies on the line. I can choose either one of these points. Okay? So the direction vector, V, is going to be the vector that goes from, I guess the way I've drawn this, I want to do head minus tail. So that's going to be 2 minus 1. 5 minus 1, and 0 minus 1. So there's the direction vector. So now, with this, with the direction vector plus any point, I'm going to choose 1, 1, 1. Any point that lies on the line, I can write down the vector equation of the line. And so it's going to look like this. R equals the position vector corresponding to 1, 1, 1 is, in angle brackets, 1, 1, 1, plus t times the direction vector, which is 1, 4, minus 1. That's it. That is the vector equation. And so now, if I want to say, or if I want to identify more points on the line, I can do that by choosing various values of t. So for example, when I choose t equals 0, that tells me that 1, 1, 1, the point 1, 1, 1 lies on the line. When I choose t equal to 1, it tells me that the point 2, 5, 0 lies on the line. If I chose t equal to 2, right, so I'd have r of 2, that's going to be 1, 1, 1 plus 2, 8 minus 2, which is 3, 9, negative 1. And so out here, that tells me that the point 3, 9, negative 1 also lies on the line. The vector form, right, is just saying that in R3, right, the position vector, all right, there's the position vector right there. That's the vector 3, 9, minus 1. All right, so there's the idea. So now, if we write R, think of that as x, y, z. R0 equal to x0, y0, z0, and the direction vector v is a, b, c. Right. So if we write these out, right, we've got our vector equation of the line. Then the vector equation R, so that's an x, comma y, comma z, equals R0, which is x0, y0, z0, plus t times v, which is a, b, c. We can pull this apart. So then the vector equation yields the three equations. So what I want to do is focus on the first component. What we have is x has to equal x0 plus t times a. So we get x equals x0 plus t times a. Focus now on the middle component, y equals y0 plus t times b. And then finally, z equals z0 plus t times c. Those three equations right here also completely determine the line, right? We can go back and forth between these three equations and this vector equation right here. These three equations together, these are called the parametric equations for L. Right, so you should be able to go back and forth between the vector equation and the parametric equations. I tend to use the parametric equations a bit more than the vector equation, right? But they give you exactly the same information. Now, in the case that A, B, and C are non-zero, then I can actually solve for t. Right? So if A, B, and C are non-zero, then solving for t gives us, so let's see, in the first one, if I solve, I'm going to get t equals x minus x0 divided by a. So t equals x minus x0 divided by a. If I solve for t in the second equation, I get y minus y0 equals b, so t is all, divided by b, so t is also equal to y minus y0 divided by b. If I do the same thing in the third equation, what I get is z minus z0 divided by c. These three equations right here, forget the t now, but they're all equal to t, which means that they're all equal to each other. These three equations right here are called the symmetric equations. Now, I don't do a whole lot with the symmetric equations, but they're in your book, so I just, just for completion's sake, that's those equations. So let's try another example. Let's find the vector parametric and symmetric equations for the line through the points, so it's going to be 0, 1, 1 and 1, 0, 1. And then as a follow-up question, at what point does this line meet the xz plane? Okay, so first of all, let's just get the vector equation. So what do we need? We need a direction vector and a point that the line passes through. So what we have, right, think of these 2 points. Here's a here's 0, 1, 1. Here is 1, 0, 1. So a direction vector can be found by going like that. Right, so there's my vector v, and so that's going to be, if I subtract head minus tail, it'll be a 1, minus 1, 0. Okay, so now r is equal to 0, 1, 1. I'm choosing that point right there, plus t times 1 minus 1, 0. I spaced out for a second. I realize now I can't ask the question, find the symmetric equations, because one of my entries right here is 0. So sorry, scratch that part. I really don't care about the symmetric equations. If all 3 of your entries in your direction vector are non-zero, you can just solve for t in all of them to write down the symmetric equations. But we can't do it in this case because I've got one of my entries equal to 0. Okay, so there is the vector equation. For the parametric equations, right? Think of this as an x, y, z. And so now what we get is x equals 0 plus t, y equals 1 minus t, and z equals 1 plus 0t. So there it is right there. Okay, so there's the equations, and now the question is, at what point does it meet the xz plane? Well, let's see, the xz plane, what is that? Well, it corresponds, right, so here's x, here's y, there's z, so the xz plane, right, is this plane that's coming out of the board. What does it mean to live in the xz plane? Well, it means that y equals 0. So for what t value does y equal 0? Well, when t equals 1. So it meets the xz plane at when t equals 1. That's going to be 1, 0, 1. So let's write down the solution. Meeting the xz plane corresponds to y equals 0. That's what it means to live in the xz plane. It means that y equals 0, which occurs when t equals 1. And so the point that we get when t equals 1 is going to be 1, 0, 1. Okay, so in the book you're going to get asked various questions about lines. They can be phrased in various ways. You've seen some of the examples here, and so now we're going to move on. The next topic, right? So we've described lines in R3. The next thing we want to do is talk about planes in R3. So what is a plane? Well, it's this flat object sitting in R3. And so what describes a plane? So imagine here's my plane, right, or at least a portion of my plane. Well, a plane is determined, or one of the facets of a plane is the way it's tilted, right? If I say I'm thinking of a plane tilted in a particular way, right? Actually, I could kind of act it out. Here's a plane tilted like this. Well, if I only tell you the tilt of a plane, there's actually an infinite number of planes that satisfy that, right? So all possible planes tilted in this same way, right? Satisfy tilt equals whatever, blah. If I say I'm thinking of a plane that's tilted in a particular way and passes through a particular point, right? Well, then we have uniqueness, right? There's a unique point. A unique plane that passes through a particular point and has a particular slant. So how would we give slant or tilt, how would we give meaning to that? Well, the way we do it is by saying, I'm thinking of a vector that's perpendicular or orthogonal to all vectors in the plane, right? So if I specify a vector and say I want the plane that is orthogonal to that particular vector, right? That completely determines the tilt. So, say it like this. So a plane in R3 is determined by a point P0 equal to x0, y0, z0 in R3, and tilt. And the way we specify tilt is by specifying a vector that is orthogonal to every vector in the plane. Okay, so let me sort of try to draw this picture here. So here is our plane. And so if I say I am thinking of the vector that's orthogonal to every vector inside the plane and specify a point P0, that completely determines my plane. So it's determined by a point P0 in R3 and a vector which is written n equal to a, b, c, that is orthogonal to every vector in the plane. Right, so no matter what, if I pick a vector in my plane, right, I get a right angle. Pick another vector in the plane, get a right angle. Pick another vector in the plane, get a right angle. Right? This vector n is called a normal vector for the plane. Right? So n is a normal vector for the plane. So now with this language, a plane is completely determined by a single point on the line and a normal vector. Okay, so let's try to actually, so my goal now is to come up with an equation that completely describes the plane. So here's the idea. Here's my plane. Let's put my axes in here now. So we're in R3. I have a point P0, and here's the idea. Whenever we have an equation for some object, whether it be a line or a plane in this case, the point of this equation is to allow us to decide which points in R3 lie on the object, in this case the plane, and which points do not, right? So okay, let's see, I've got P0. Now let's take another point, P. So suppose P equal to the point X, comma Y, comma Z lies on the plane. Now what I want to do is I want to join or not join. Well, okay, yeah, I want to go from the origin to those points. Those are the position vectors corresponding to P0 and P. And let's call them, I guess I probably want to call them R0 and R. So this is the vector R0, and this is the vector R. Move my P0 over to there. Now, now what? Let's let that be. So what do I want to call that one? I guess I don't need to give it a name. This vector right here is R minus R0. And so observe that, okay, so this vector lies in the plane, which means that it is orthogonal to the vector n. So observe that R minus R0 is orthogonal to n. And so, okay, how do we check for orthogonality? We use the dot product, right? And so what that tells us is that n dot R minus R0 has to equal 0. So let's write that out. I know I'm erasing this, but we know who R and R0 and N are. So what we have is A, B, C dot, so that's going to be X minus X0, comma Y minus Y0, Z minus Z0 has to equal 0. And then let's write this out. So this is going to be, when I take the dot product, A times X minus X0 plus B times Y minus Y0 plus C times Z minus Z0 equals 0. Oh, look, we have an equation now. Now, it's typically solved out here, so I'm going to multiply things out. AX plus BY plus CZ. Now, then I also have an A times X0, negative, plus or minus B times Y0 minus C times Z0. I don't want to move all that stuff over to the other side of the equation. So this is going to be A X0 plus B Y0 plus C Z0. And I want to call this little d, right? So the standard equation for a plane is right there. Equation of a plane. So here's the idea then. If you know a normal vector and a single point that lies on the plane, you can basically just write down the equation of the plane. And I mean, I actually don't really care. In many cases, it's sufficient to just write it down like, in fact, maybe it's even preferred sometimes to write it down like that. There's times, I mean, it's going to be given to you in this way, so you need to be able to go back and forth between the two. But either one of those is actually acceptable to me. So, for example, let's find the equation of the plane with normal vector n equals 1, 2, 3. Oh, no, sorry, that's the point that it passes through. Okay, so normal vector, negative 2, 7, 4. Negative 2, 7, 4, passing through a point 1, 2, 3. If you have this information right here, you can just write down the equation of the plane. It's going to be minus 2 times x minus 1 minus 2 x minus 1 plus 7 times y minus 2. 7 times y minus 2. Plus 4 times z minus 3 equals 0. There it is. Now, questions involving, now in your homework you're going to get a bunch of questions involving lines and planes, right? And so these questions can be phrased in various ways. And so I want to give you a few of the different types of problems that can be asked. Let's see what time we got here. So let me do a few examples here. One thing that I think you know, if you know 3 points that don't lie on the same line, any 3 points determine a plane. Okay? So this next question is going to use that fact. So it goes like this. Does the point 2, 1, 2 lie on the plane determined by 0, 0, 0, 1, 1, 1, 1, and negative 1, 2, 0. So here's the idea, right? I've got a plane that contains these 3 points, right? So here's 0, 0, 0. I'm just trying to draw in a schematic of this 1, 1, 1 and minus 1, 2, 0. And so here's my plane, and then the question is, does this point 2, 1, 2 lie on the plane or not? So to answer that question, here's what I want to do. I would like to find the equation of the plane, and then see if this point right here satisfies the equation of the plane. If it satisfies it, the answer is yes. If it doesn't satisfy the equation, then the answer is no. All right, so we've got these 3 points. To write down the equation of a plane, you need a normal vector and a single point that lies on the plane. We've got 3 points that lie on the plane. We still need a normal vector. How are we going to do that? Well, here's how we do it. Notice that these 3 points determine 2 vectors. Call them u and v. If we want a point, a vector that's orthogonal to every vector in there, well then it needs to be orthogonal to u and v, and we have a way to compute a vector that's orthogonal to both u and v. And so to find a normal vector, all we need to do is compute u cross v. That will give us a normal vector. So u equals 1, 1, 1. V equals minus 1, 2, 0. And so n, that's going to be u cross v, or v cross u, whichever one you want to use. And so that's going to be, let's see, negative 2, 1, or 0, minus negative 1 gives me plus 1, but because it's the middle coordinate, negate it. And then the last one is going to be 2 plus 1, so that'll be a 3. So here's our normal vector. Now I can choose any one of these 3 points and write down the equation of the line. I might as well choose that one right there. It makes life the easiest. And so now what we get is minus 2 times x minus 0, minus 1 times y minus 0, plus 3 times z minus 0 equals 0. And then we take our point 2, 1, 2, we plug it in and see if it satisfies it or not. I just want to check and make sure it looks a little weird here. Let me see. So negative 2, 1 minus negative 1 gives me positive 1, so I negate it. And then I have a 2 minus negative 1 is which is positive 3. Yeah. Okay, so now if I plug a 2 in here, so I'll get a minus 2 times 2, minus 1 plus 3 times 2. So that's a negative 4, negative 5 plus 6 equals 1, which is not equal to 0. And so the answer is no. It does not satisfy the equation of the plane, which means it does not lie on the plane. There will be some questions that involve the angle between two planes. So the angle between planes is the angle between their normal vectors. So if you get a question that asks about the angle between two planes, this is what you do. You find the normal vectors and compute the angle. So for example, let's find the angle between the planes x plus y plus z equals 1 and 2x plus y minus z equals 2. Okay, so the normal vector here, let's say n1, is going to be the vector 1, 1, 1. The normal vector here, let's call it n2, is going to be 2, 1, minus 1. Notice, when you have the equation of the plane, you can just read the normal vector off from the equation by just taking the coefficients of x, y, and z. Okay, so now we need the angle between n1 and n2. Let's see, how do we find the angle? Well, the cosine of theta is equal to n1 dot n2, so that's going to be 2 plus 1 is 3 minus 1, so that gives us a 2, divided by the length, so that will be the length of n1 is a root 3, and the length of this one, that's going to be a 4, 5, 6. So what is that? That's a 2, 3 root 2. Does that come out to be anything nice? Root 2. Yeah, okay, this is not a nice angle. Yeah, because it's root 2 over 3. That's nothing. Okay, so let me simplify this a little bit. This is going to be the 2's will cancel here, so it'll be a root 2 over 3. And so the angle is going to be the inverse cosine of root 2 over 3, whatever that is, right? If you need, you could plug that in your calculator to find who that is. So in your book, there's a homework problem that tells you how to find, or it gives you a formula, basically, for the distance between a point and a line. There's also a homework problem that gives you the distance between a point and a plane. Now, if you want, you can just memorize that formula, but I don't really recommend that. I recommend actually understanding how it goes for these. So these next two examples I want to do are going to involve that, right? So let's first say, let's find the distance between the point 1, 1, 1 and the line r equals 1, 2, 3 plus t times 1, 0, 1. So, like I said, you can memorize the formula that tells you how to do this, and it makes it a little bit quicker, but depending on how I phrase the question, I think it's important to understand the process behind this. So my advice would be to understand what's going on here. And so here's the idea. All right, I've got the point 1, 1, 1. And what we're looking for, when we say the distance, what we're really looking for is the distance, right? If you drop a perpendicular and see which point that is, and then measure the distance between that point and that point. That's what we mean by the distance between the point and the line. It's really the minimal distance. And a perpendicular is what minimizes the distance. Okay, now All right, so how are we going to identify that point? And that will be the process. We're going to identify the closest point on there and then just use the distance formula to measure the distance between. Now, any point on this line, if you think in terms of parametric, any point on this line is of the form 1 plus t, 2, and 3 plus t. All right? So here's the idea. What I'd like to do is look at that vector. Which way do I want to draw it? Yeah, that's fine. And then there's also the direction vector of the line, which lives inside the line. So what we're looking for, right, each time I choose a new point, I can create, or look at the direction vector, and I'm looking for the one that gives us orthogonality. So I want to create a vector that goes from a point on the line to that point right there, right? And we'll just do a head minus tail subtraction. And then compute the dot product between that vector and our direction vector, right? 1, 0, 1. When we get a dot product equal to 0, that will identify the t that gives us orthogonality. That will tell us the t for the point that lives on that plane. Sorry, on that line. Okay, so let me say all of that. So, right, so a point on the line is of the form, so it'll be 1 plus t, comma 2, comma 3 plus t, which means that the vector, right, so the vector from this point to 1, 1, 1 is, so it's going to be 1 minus this will give us negative t. All right, so it's 1 minus here. And then it's going to be 1 minus 2, so that gives me a negative 1. And then it's going to be 1 minus quantity 3 plus t, that's a negative 2 minus t. Right, so that is who this vector is right there. So distance is minimized when negative t, comma minus 1, comma minus 2, minus t, dot the direction vector, which is 1, 0, 1, equals 0. In that case, right, so here's my direction vector, or a representation of the direction vector, and then here would be that vector, right, so we're looking for the t that gives us that right there. So that's going to be minus t minus 2 minus t has to equal 0, right, I just took the dot product there. And so it looks like, let's see, bring the, so that's a negative 2t minus t. So that means that t has to equal minus 1. So the point on the plane, when t equals minus 1, is going to be 0, 2, 2. So nearest point is going to be, okay, if t equals negative 1, it's going to be 0, 2, 2. So now, what's the distance between this point and this point, which we've discovered is 0, 2, 2? I'll just use the distance formula. So the distance is going to be square root of 1 squared, 1 minus 2, and then 1 minus 2, all of that squared. So we get a square root of 3. So here's the idea, let me just reiterate, right? You're trying to find the vector from the point up to the given point, right? So from a point on the line to the given point, that gives us a right angle here, and so we just solve for t to find which t value gives us that vector. All right, so now I want to do one that measures distance between point and plane. So let's find the distance between the point one, 1, 1, and the plane is going to be x plus 2y plus z equals 1. So x plus 2y plus z equals 1. All right, so this is going to be the same idea in the sense that we want to find the point that minimizes the distance, and then we're going to measure the distance between these 2 points. Of course, now we're dealing with a line versus a plane, and so here's what I'm going to do. I would like to create a line that passes through 1, 1, 1 and meets the plane orthogonally. And then I want to find the intersection of the line and the plane. That will give me that point right there. So, how do I find the equation of a line? Well, I need a point that it passes through and a direction vector. What should the direction vector of this line be? Well, we want this line to be orthogonal to the plane, which means we should choose the normal vector for the plane to be the direction vector for the line. So the line through 1, 1, 1, orthogonal to the plane, has direction vector equal to the normal vector for the plane. And who is the normal vector for the plane? Well, we can just read it off. It's 1, 2, 1. So, in parametric form, the line is going to be x equals 1 plus t, y equals 1 plus 2t, and z equals 1 plus t. Okay, so here's the parametric equations for the line that passes through 1, 1, 1 and hits the plane or meets the plane orthogonally. Now we want to find the intersection of this line with this plane. So this set of equations right here describes all possible points on the line. We want the point that hits the plane, which means it has to satisfy this equation. So I'm going to substitute the parametric equations into the equation of the line to find the t value. Right, that gives us intersection. So now sub into the plane equation. So we're going to get 1 plus t plus 2 times 1 plus 2t plus 1 plus t equals 1. So that's going to be t, 4t, 5t plus 1, 2, 4 plus 4 equals 1. Is that right? 1 plus 2 is 3 plus 4. Yeah. So subtract over, that's a negative 3. So t equals negative 3/5. Now that's not the best t value in the world. Okay, so the intersection point now, I need to come back up here and substitute. So intersection, okay, so that's when t equals negative 3/5. So that's going to be 2/5, negative 3/5. 1 minus 6/5 is just 1/5, right? Negative. Did I get that right? 1 minus 6/5. Yeah, negative 1/5. And then another 2/5, right? 1 minus 3/5. Yeah. Okay, so the intersection occurs there. And so the distance, right? So this is my point, 2/5, comma, negative 1/5, comma, 2/5. So the distance, right, if we use the distance formula, from this point to this point is going to be 1 minus 2/5, which is 3/5 squared, plus 1 minus 1/5, 1 minus negative 1/5, so that'll be 6/5, so 6/5 squared, plus 1 minus 2/5 is 3/5, so plus 3/5 squared. And so what do we get here? I don't really want to write all this out. 9 25ths plus 36 25ths plus 9 25ths. 36 plus 18 is 54, which is 9 times 6. Okay, so this is going to be square root of 54 over 25. That's going to be 3 root 6 over 5 in simplified form. Okay, so that's a lot for today, and I think that's enough. Your homework is going to ask you to do various things with lines and planes. If you understand the construction of a line and a plane, right, then each of these problems, by just sort of breaking it down into little pieces, is doable. Okay, so we will see you next time.